The night of November 15, 1940, a Bristol Blenheim fighter lifted off from RAF Tangmere into absolute darkness. Inside the cramped cockpit, Flight Lieutenant John Cunningham and his radar operator Sergeant John Phillipson hunted for German bombers raiding British cities. Behind them, crammed into the fuselage, sat a machine that most senior RAF commanders believed would never work. The air interception Mark III radar occupied nearly half the available space, its bulky transmitter and receiver units connected to a tangle of wires and crude antennas protruding from the aircraft's nose. The two cathode ray tubes glowed green in the darkness, showing nothing but electronic noise and ground clutter. This equipment had been called unreliable, temperamental, even impossible. Fighter Command had waited 4 years for a working airborne radar. What they received instead was a device that failed more often than it functioned, required extraordinary skill to operate, and frustrated even its most dedicated advocates. Yet, on this particular night, through a combination of luck, skill, and the desperate determination of its operators, this unreliable machine would guide Cunningham to his target. The resulting victory would prove that the future of night fighting belonged not to pilots with exceptional eyesight hunting by moonlight, but to electronic eyes that could see through darkness itself. What the RAF and Luftwaffe commanders did not yet fully understand was that this crude, unreliable radar would evolve within months into a weapon that would render German night fighters completely blind to the aircraft hunting them, transforming a technological weakness into a devastating advantage. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The story of airborne interception radar began not with military urgency, but with bureaucratic skepticism and the determination of one Welsh physicist. In 1936, Henry Tizard, chairman of the Committee for the Scientific Survey of Air Defence, sent a memo to Robert Watson Watt, director of Britain's radar research efforts. The memo addressed what Tizard considered the most critical gap in Britain's air defence system. The recently developed chain-home early warning radar could detect incoming bombers at distances exceeding 100 miles. Ground controllers could plot their courses and scramble interceptors accordingly. But once German bombers began attacking at night, as everyone assumed they eventually would, British fighters would face an impossible task. Finding a specific bomber in the vast darkness of the night sky, even when directed to the general area by ground control, amounted to searching for a needle in a haystack while flying at 250 miles per hour. Watson Watt agreed to allow Edward George Bowen, a young physicist universally known by his nickname Taffy, to form a small team to investigate the possibility of miniaturizing radar technology for installation in aircraft. Bowen was 24 years old, brilliant, and possessed the kind of determined optimism that would prove essential for a project that senior engineers declared impossible. The challenge seemed straightforward to state but extraordinarily difficult to solve. The chain-home radar installations occupied entire buildings, consumed enormous amounts of electrical power, required massive antennas mounted on steel towers 350 feet tall, and needed constant adjustment by trained operators. Converting this technology into something that could fit inside an aircraft, operate reliably at altitude, survive the vibration and temperature extremes of flight, and be operated by a single crew member represented a technological leap that most experts considered beyond the capabilities of 1930s engineering. Bowen's team at Bawdsey Manor on England's east coast began their work in late 1936, working with equipment that would be considered primitive by any standard. The transmitter used vacuum tubes that generated barely enough power to detect large objects at very short ranges. The receiver electronics were so insensitive that detecting the faint echoes from distant aircraft proved nearly impossible. The antennas, mounted externally on test aircraft, created enormous aerodynamic drag and frequently broke loose during flight. Early test flights in 1937 and 1938 produced results that ranged from disappointing to disastrous. The team attempted to detect other aircraft during carefully arranged test flights, where both the target aircraft and the radar-equipped aircraft knew exactly where the other should be. Under these ideal conditions, with cooperative targets flying predictable courses in good weather, the radar frequently failed to detect anything at all. In a development that would prove both fortunate and frustrating, the team discovered their radar could easily detect large ships and coastal features. While testing an early system near Bawdsey Manor, Bowen's team failed to detect any aircraft but clearly saw cranes, buildings, and ships at nearby docks. Further experiments demonstrated the ability to track Royal Navy capital ships in terrible weather at ranges of several miles. This discovery immediately attracted intense interest from RAF Coastal Command and the British Army, both of whom saw applications for detecting enemy shipping. The Air Ministry, desperate for any technology that might provide military advantage, directed Bowen's team to prioritize development of air-to-surface vessel radar, designated ASV, for detecting submarines and ships. Work on the aircraft interception problem largely ended. It would not resume in earnest until 1939, with war clearly imminent and the night bomber threat becoming impossible to ignore. The delay would prove costly. When war began in September 1939, Bowen's team had produced prototype ASV radars that worked reasonably well for detecting ships. Their AI radar development had advanced little beyond the experimental stage. The equipment remained unreliable, temperamental, and difficult to operate. Maximum detection range against aircraft remained limited to around 2 miles under ideal conditions. Minimum range, the closest distance at which the radar could detect a target, extended to approximately 1,000 feet, far too long to allow easy interception. This minimum range problem stemmed from a fundamental technical limitation. The transmitter signal did not turn off cleanly. Instead, it leaked through to the receiver, causing the receiver circuits to oscillate or ring for a brief period. While this powerful signal gradually died down, reflections from nearby aircraft were completely lost in the electronic noise. Numerous solutions had been attempted throughout 1938 and 1939. None proved satisfactory. The problem persisted, frustrating engineers and pilots alike. The equipment's unreliability manifested in multiple ways that would have defeated any project with less determined advocates. Vacuum tubes, the electronic components that powered both transmitter and receiver, frequently failed due to vibration during flight. The technology of the late 1930s had not yet produced tubes capable of withstanding the constant shaking of piston-engine aircraft. Tubes that worked perfectly on laboratory benches often failed within hours of installation in aircraft. Connections loosened, solder joints cracked, and components that should have lasted for months failed after a few flights. The crude cathode ray tube displays, adapted from early television technology, proved nearly impossible for operators to interpret. Unlike modern radar displays that show clear images of targets, these early systems produced dim green, blips on small screens covered with electronic noise, ground clutter, and artifacts. Distinguishing an actual aircraft return from the chaos of spurious signals required months of training and exceptional skill. Many radar operators never achieved proficiency despite extensive instruction. The external antennas created serious problems for aircraft performance. Mounted on the nose and wings of test aircraft, these ungainly arrays of wires and poles increased drag significantly. The added drag reduced maximum speed, decreased range, and made the aircraft less maneuverable. Pilots complained that the radar equipment turned capable fighters into sluggish, vulnerable targets. Moreover, the antennas frequently broke during flight, rendering the radar useless while simultaneously creating dangerous flying conditions. Loose antenna wires could damage control surfaces, become entangled with the aircraft structure, or create unpredictable aerodynamic effects. In September 1939, as war began, the entire radar research establishment at Bawdsey Manor was evacuated overnight to a pre-arranged location at the University of Dundee in Scotland. This move, designed to protect critical research from potential German attacks, instead created chaos that would delay AI radar development for crucial months. Watson Watt had arranged the evacuation to Dundee largely because it was his alma mater. He had made little effort to prepare the university for AMES arrival, and the rector was surprised when dozens of scientists and technicians appeared one day without warning. Almost no laboratory space was available as students and professors had returned from summer holidays and occupied all facilities. The AI team was sent to a small private airfield at Perth, miles away from the main research group. The location was entirely unsuitable for development work. Both facilities lacked adequate heating, laboratory equipment, and workshop capabilities. The teams constantly complained about the impossible working conditions. Bowen and his colleagues attempted to continue development work while literally freezing in unheated hangars during the Scottish winter. Progress slowed to a crawl. Albert Percival Rowe, who had replaced Watson Watt as head of the radar research teams, had a troubled relationship with Bowen and many others at AMES. Personality conflicts and disputes over priorities created additional friction at precisely the moment when unity of purpose was most needed. The Air Ministry, watching the deteriorating situation, made a decision that would prove nearly fatal to the AI radar program. Desperate to field any night fighting capability, they pressured AMES to begin immediately equipping aircraft with the prototype Mark II AI systems, despite knowing these units were nowhere near ready for operational use. The Mark II had been hand-built in extremely limited numbers. Each unit was essentially unique, incorporating different components and requiring individual calibration. Reliability remained abysmal. The equipment worked intermittently under laboratory conditions and failed even more frequently when subjected to the rigors of operational flying. Nevertheless, in late 1939 and early 1940, RAF squadrons began receiving Bristol Blenheim fighters equipped with AI Mark II radar. The results confirmed every pessimistic prediction. The radar failed constantly. Maintenance crews lacked training and spare parts. Operators struggled to extract any useful information from the unreliable displays. Pilots questioned whether the equipment provided any advantage whatsoever given its weight penalty and the drag created by its external antennas. Fighter Command's commander, Air Chief Marshal Hugh Dowding, examined the early AI-equipped Blenheims with growing concern. When Watson Watt claimed he could provide hundreds of working radar sets, Dowding famously demanded instead 10 that actually work. His skepticism reflected harsh reality. The AI-equipped night fighter force of early 1940 was largely ineffective. Interception rates remained abysmal. Through the winter and spring of 1940, as German bombing attacks on British targets increased, AI-equipped fighters shot down virtually no enemy aircraft. The radar's unreliability meant most sorties involved pilots and operators struggling with malfunctioning equipment rather than hunting German bombers. When the equipment did function, its limitations made successful interceptions extraordinarily difficult. Maximum detection range of approximately 2 miles meant the fighter had to be vectored to within a very small volume of airspace before the radar operator could even see the target on his display. Ground controllers using chain-home radar could determine bomber positions only within several miles, far too imprecise for effective vectoring. Once detected on the AI radar, targets frequently disappeared from the display as they flew outside the radar's limited field of view. The radar operator had to continuously adjust controls, interpret ambiguous returns, and provide directions to the pilot based on information that was often unclear or contradictory. The pilot, meanwhile, had to maintain precise formation flying while handling an aircraft whose performance was degraded by the radar equipment's weight and drag. Reaching a position where visual contact could be established required extraordinary coordination between pilot and operator, usually in turbulent clouds or darkness with poor visibility. The minimum range problem created a particularly dangerous situation. When the fighter finally closed to within 1,000 feet of the target, the radar suddenly went blind as the transmitter's ringing obscured the target return. The pilot had to transition from instrument flying based on radar guidance to visual flying in darkness or clouds, searching desperately for a bomber that might be anywhere within a sphere, roughly 1,000 feet in radius. Frequently, by the time visual contact was established, if it was established at all, the bomber had maneuvered away or the fighter had overshot. Night after night through the spring of 1940, AI-equipped fighters flew sorties that accomplished nothing. The equipment failure rate exceeded 50%. Successful interceptions remained so rare they were celebrated as exceptional achievements. Senior RAF commanders began questioning whether airborne radar would ever provide a practical solution to the night bomber threat. Dowding's dismissal from Fighter Command in November 1940 was influenced in part by his insistence on waiting for AI radar to mature rather than pursuing alternative night fighting methods. Many historians have argued his dismissal was unwise, that his identification of AI radar as the only practical long-term solution was ultimately correct. But in the dark months of 1940, with German bombers destroying British cities night after night and AI-equipped fighters achieving almost no results, the criticism appeared well-founded. The interception rate through late 1940 remained at approximately 0.5%. For every 200 sorties flown by AI-equipped night fighters, one resulted in an enemy aircraft being shot down. This represented an extraordinarily poor return on the substantial investment in radar development, aircraft modification, and crew training. Alternative methods, including fighters with pilots selected for exceptional night vision patrolling known bomber routes, achieved similar or better results with far less complexity. Some RAF leaders argued that sophisticated technology was not the answer, that traditional methods refined through training and experience would prove more effective. The breakthrough that would transform this unreliable technology into a war-winning weapon came not from Bowen's increasingly frustrated team, but from an unexpected source. EMI, the electric and musical industries company, better known for manufacturing phonographs and early television equipment, had been peripherally involved in radar development through their electronics expertise. In early 1940, EMI engineers proposed a fundamentally different approach to solving the minimum range problem that had plagued AI radar since its inception. Rather than using a self-exciting transmitter that oscillated continuously and leaked signal into the receiver, EMI developed a new transmitter design based on a separate squegging oscillator. This device produced clean pulses of the carrier signal using a precision timer. The same timer simultaneously muted the receiver during transmission, completely eliminating the ringing issue that had created the blind spot at close range. The solution was elegant in its simplicity, though implementing it required sophisticated engineering. By June 1940, EMI had produced working prototypes that reduced minimum range from 1,000 feet to approximately 400 feet. This represented a dramatic improvement, though still not ideal. 400 feet remained uncomfortably close for a pilot attempting to acquire visual contact with an enemy bomber in darkness while traveling at over 200 miles per hour. Nevertheless, the improvement was substantial enough that the Air Ministry authorized production. The new system, designated AI Mark IV, went into production in July 1940. All units were allocated to the newly arriving Bristol Beaufighter, a heavy fighter that had been specifically designed with sufficient size and power to carry radar equipment without crippling performance penalties. The Beaufighter represented everything the Blenheim was not. Where the Blenheim was slow, barely capable of catching German bombers, the Beaufighter could reach 320 miles per hour even when loaded with radar equipment. Where the Blenheim was lightly armed, the Beaufighter carried 4 20mm Hispano cannons and 6.303 machine guns, the heaviest forward-firing armament of any Allied fighter when it entered service. Where the Blenheim was cramped, the Beaufighter provided adequate space for the radar operator to work without being jammed against equipment and bulkheads. The combination of improved radar and improved aircraft began to show results in late 1940, though progress remained frustratingly slow. The first AI Mark IV equipped Beaufighter victory occurred on the night of November 15th to 16th, 1940, when an aircraft from No. 604 Squadron destroyed a Junkers Ju-88 near Chichester. This single success generated enormous excitement within Fighter Command, finally providing concrete evidence that the concept could work. But one victory did not constitute an effective night fighter force. Through December 1940 and January 1941, interception rates remained barely above the levels achieved with the Unreliable Mark II and Mark III systems. The problem was no longer primarily technical, though the Mark IV still suffered reliability issues. The fundamental challenge had shifted from making radar work to using radar effectively. Fighter Command discovered that airborne radar alone could not solve the night fighter problem. The missing element was precision ground control. Chain-home radar could detect incoming bomber formations at long range, but its angular accuracy was insufficient to guide fighters to within the 2 to 3 mile detection range of AI Mark IV. Ground controllers knew roughly where German bombers were flying, but roughly was not precise enough. Fighters scrambled based on chain-home information, often found themselves searching empty sky, their AI radar seeing nothing because the bombers were miles away from where ground control had predicted. What was needed was a ground-based radar system with Purd-Keen's boutiz, both the range of chain-home and sufficient angular accuracy to guide fighters to within AI detection range. In November 1939, Robert Hanbury Brown, one of the radar operators working with Bowen's team, had suggested a revolutionary new type of ground radar display. Instead of showing targets as blips on a linear trace, his proposed system would show both targets and friendly fighters simultaneously on a map-like display. Ground controllers could then directly guide fighters onto intercept courses by watching the relative positions of both aircraft. The concept required rotating the radar antenna continuously through 360 degrees, while simultaneously rotating the display at the same rate. Each time the rotating beam swept past a target, the target would appear briefly on the display at the correct bearing and range. The result would be a true map view of the surrounding airspace, showing all aircraft within range. Development of this ground control interception system, abbreviated GCI, proceeded through 1940 in parallel with AI radar development. By late 1940, prototype units existed and demonstrated impressive capabilities. 6 hand-built GCI radars went operational in January 1941, with the first station at RAF Sopley becoming active on New Year's Day. The combination of GCI ground control and AI Mark IV airborne radar transformed night fighting effectiveness almost overnight. For the first time, the system worked as originally envisioned. Ground controllers using GCI radar could see incoming bomber formations and friendly night fighters simultaneously. They could vector fighters precisely onto intercept courses, guiding them to within 2 miles of the target. At that point, the AI radar operator acquired the target on his display and took over, directing the pilot through the final interception until visual contact was established at ranges of 400 feet or less. The statistical evidence of transformation was dramatic. Prior to GCI deployment in December 1940, interception rate remained at approximately half of 1%. By May 1941, with multiple GCI stations operational and crews gaining proficiency, interception rate had climbed to 7%. More significantly, the kill rate, the percentage of interceptions that resulted in enemy aircraft destroyed, reached approximately 2.5%. These numbers might appear modest, but they represented exponential improvement over previous performance. Night fighter kills increased geometrically through the spring of 1941. In January, 3 German bombers were shot down by AI-equipped fighters. February saw 4 kills. March brought 22. April produced 48. In May, 96 German bombers fell to AI-equipped Beaufighters. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The Luftwaffe, which had been bombing British cities with relative impunity for months, suddenly faced a night fighter force that was finding and destroying bombers with increasing efficiency. By June 1941, AI-equipped fighters accounted for almost all night fighter kills. Traditional methods, including the so-called cat's eye fighters flown by pilots with exceptional night vision, had been completely eclipsed. The technology that senior commanders had dismissed as unreliable and impractical was now destroying German bombers faster than the Luftwaffe could replace them. The psychological impact on German bomber crews was profound. Throughout late 1940 and early 1941, German bombers had operated in the comfortable knowledge that British night defences were largely ineffective. Losses to night fighters had been minimal. Anti-aircraft fire and accidents caused more casualties than enemy action. Bomber crews could focus on finding and flafe, attacking their targets rather than constantly watching for fighters. Beginning in April and accelerating through May 1941, this comfortable situation evaporated. German bombers began disappearing with alarming regularity. Crews that survived attacks described British fighters appearing from darkness without warning, opening fire with devastating effect, then vanishing before defensive gunners could respond. The attacks seemed impossible to predict or counter. No amount of vigilance by lookouts could spot fighters approaching through total darkness until cannon fire and tracers revealed their presence. By that point, survival depended entirely on luck. The Luftwaffe had no effective response. Germany's airborne radar development lagged approximately 2 years behind Britain's. While RAF scientists had been working on AI radar since 1936, Germany had not seriously pursued airborne interception radar until 1939. The first German AI system, designated Liechtenstein BC, did not enter operational service until early 1942. Even then, production remained limited, and the equipment suffered many of the same reliability problems that had plagued early British systems. More fundamentally, German air defense doctrine had not prioritized airborne radar development because Germany's strategic situation differed dramatically from Britain's. Major targets in Germany, after the occupation of France in 1940, were located hundreds of miles from Allied air bases. German early warning radar provided long notice of approaching bombers. This extended warning time allowed German defenses to rely on ground-based systems. The Kammhuber Line, established in mid-1940, divided German-controlled airspace into defensive zones. Each zone contained searchlight batteries and ground-based radars that tracked both bombers and defending fighters. Ground controllers directed fighters to intercept positions, then searchlights illuminated the bombers, allowing fighters to attack visually without requiring airborne radar. This system worked reasonably well against the small, scattered raids that RAF Bomber Command conducted through 1940 and 1941. Individual bombers or small formations could be tracked, illuminated, and engaged with acceptable efficiency. The system's fundamental weakness, which would become catastrophically apparent in later years, was limited capacity. Each defensive zone could handle only 1 or 2 interceptions simultaneously. A large, concentrated bomber stream could overwhelm the defenses simply by saturating the available zones. But through 1941, RAF Bomber Command lacked the strength and coordination to exploit this weakness. German night fighters in 1940 and 1941 thus operated blind in a sense entirely different from what British bombers experienced. German fighters were not blind due to technological inferiority. Their aircraft were excellent, their pilots skilled, their tactics sound. They were blind because they operated in a tactical environment where visual acquisition remained the only method of final target identification. All the sophisticated ground control, all the searchlights and zone defenses ultimately depended on German pilots seeing British bombers with their own eyes before attacking. If weather conditions prevented visual acquisition, if searchlights failed to illuminate targets, if bombers flew routes that avoided the defended zones, German night fighters accomplished nothing despite their presence in the sky. British night fighters, by contrast, hunted with electronic eyes. Weather that would have completely negated German defences merely reduced British effectiveness. Darkness that rendered visual searching hopeless presented no obstacle to radar. The transformation was profound and would only accelerate as radar technology continued to improve. The AI Mark IV, despite representing a revolutionary advance over earlier systems, still suffered significant limitations. Its maximum range remained tied to aircraft altitude, typically around 4 miles when flying at 15,000 feet. The radar's relatively long wavelength of 1.5 meters meant it used large, poorly directional antennas that broadcast energy across the entire forward hemisphere of the aircraft. This omnidirectional pattern meant the radar saw everything in front of the fighter, including ground returns that cluttered the display and made low-altitude interceptions nearly impossible. When flying at low altitude, ground reflections completely swamped returns from aircraft, rendering the radar useless below about 5,000 feet. This limitation became critically important in late 1941 when the Luftwaffe began low-level attack missions. German bomber crews, recognizing that British night fighters were most effective at medium and high altitudes, began approaching targets at extremely low level where AI Mark IV was blind. The RAF needed a solution, and the solution required entirely new radar technology operating at much shorter wavelengths. The breakthrough technology that would render German night fighters completely blind while making British night fighters even more deadly had been invented in early 1940 but required 2 years of intensive development before reaching operational status. At Birmingham University, physicists John Randall and Harry Boot had developed the cavity magnetron, a revolutionary device capable of generating powerful microwave radiation at wavelengths of approximately 10 centimeters. This was a dramatic reduction from the 1.5-meter wavelength used by AI Mark IV. Shorter wavelengths offered enormous advantages for radar applications. Antennas could be much smaller while remaining highly directional. A parabolic dish 30 inches in diameter, small enough to fit in an aircraft nose, could create a narrow, focused beam at 10-centimeter wavelength. The same directional characteristics would require an antenna over 15 feet in diameter at 1.5-meter wavelength, impossible to mount on any aircraft. Narrow beam radar eliminated ground clutter problems. By pointing the antenna above the horizon, the radar would not see ground returns at all. Aircraft at any altitude above the fighter could be detected without interference from ground reflections. Higher operating frequency also meant greater inherent accuracy in measuring range and bearing. The cavity magnetron's development by Randall and Boot represented one of the most significant technological breakthroughs of World War II. Its impact would extend far beyond immediate military applications, ultimately enabling technologies, including satellite communications, television broadcasting, and microwave ovens. But in 1940 and 1941, its military potential dominated all considerations. The TISAD mission of September 1940 carried a cavity magnetron to the United States as part of the most significant technology transfer of the war. Bowen himself escorted the device, locked in a secure container, and presented it to American scientists and engineers. The Americans, who had nothing comparable, immediately recognized its revolutionary potential. Within months, a dedicated laboratory, the Radiation Laboratory at MIT, was established to develop microwave radar systems. American industrial capacity would ultimately produce cavity magnetrons by the tens of thousands, equipping Allied aircraft and ships with radar capabilities that Axis powers could not match. British development of microwave airborne radar proceeded in parallel. Bernard Lovell, who would later become famous for radio astronomy, led the team developing what became known as AI Mark VIII. The project combined the cavity magnetron with a rotating parabolic antenna and a new type of display that showed a target position relative to the aircraft. Development proved challenging despite the superior technology. The scanning antenna mechanism required precision manufacturing. The nose of aircraft had to be modified with radome, transparent to radio waves but strong enough to withstand flight loads. Numerous technical problems delayed introduction. Nevertheless, by late 1941, prototype systems demonstrated remarkable capabilities. Detection range against bombers reached 5 miles or more regardless of altitude. The radar could detect aircraft flying below the fighter's altitude by pointing the antenna downward, something AI Mark IV could never accomplish due to ground clutter. Minimum range dropped below 200 feet, giving pilots more time to acquire visual contact. Most significantly, the narrow beam meant the radar operator could precisely locate targets in 3 dimensions, making interception much easier. The first operational AI Mark VIII systems reached squadrons in early 1942, equipping both Beaufighters and the new de Havilland Mosquito night fighter. The Mosquito, constructed primarily of wood to conserve strategic materials, proved to be one of the finest aircraft of the war. Fast enough to outrun most German fighters, maneuverable enough to dogfight despite its twin-engine configuration, and possessing exceptional range, the Mosquito became the preferred mount for night fighter crews. Armed with AI Mark VIII radar and 4 20mm cannons, Mosquito night fighters began operations in mid-1942. The combination proved devastatingly effective. Mosquitoes could patrol for hours, their long range allowing coverage of vast areas. Their speed meant they could pursue targets that might escape slower bowfighters. Their AI Mark 8 radar allowed them to find targets in any weather, at any altitude, with far greater reliability than earlier systems. German bomber losses increased sharply wherever Mosquitoes operated. More ominously for the Luftwaffe, AI Mark 8-equipped Mosquitoes began hunting German night fighters. British intelligence had identified emissions from German Liechtenstein radar, which finally began appearing in significant numbers on Luftwaffe night fighters in mid-1942. A system called Serat allowed British night fighters to home in on Liechtenstein radar emissions from dozens of miles away. Mosquitoes would patrol areas where German night fighters operated, detect Liechtenstein radar signals, follow those signals to their source, then use AI Mark 8 to close to firing range. German night fighter pilots suddenly found themselves being hunted by an enemy they could neither see nor detect. Their own radar emissions, meant to help them find British bombers, instead marked them for destruction by British fighters whose electronic eyes saw perfectly in darkness that blinded German crews. The situation created a devastating asymmetry. German night fighters attempting to intercept British bomber streams had to turn on their Liechtenstein radar to find targets. The moment they activated their radar, they became visible to British intruder aircraft carrying Serati. German pilots faced an impossible choice: operate without radar and remain effectively blind, unable to find bomber targets, or turn on radar and risk becoming targets themselves. Many German night fighter aces died, never seeing the mosquito that killed them, shot down by cannon fire that came from darkness without warning. The psychological impact was severe. The hunters had become the hunted, and they possessed no defense against an enemy whose technological advantage was overwhelming. By 1943, the technological gap had widened to a chasm. British AI radar had evolved through multiple generations, each offering improved performance and reliability. German Liechtenstein radar, just entering widespread service, still suffered from reliability problems similar to those that had plagued British AI Mark III in 1940. More crucially, British electronic warfare capabilities had advanced to include not just detection of German radar emissions, but also active jamming. The system called Window, consisting of strips of aluminum foil cut to precise lengths, could completely blind German radar when dropped in sufficient quantities. German ground control radar, German gun-laying radar, German Liechtenstein airborne radar, all became useless when British bombers began dropping Window in July 1943 during the Battle of Hamburg. The German radar screens filled with thousands of false returns, each strip of foil appearing as a bomber target. Ground controllers could not determine which returns represented actual bombers and which were chaff. German fighters, directed to intercept what radar showed as dense bomber formations, found only clouds of slowly drifting foil strips. Actual bombers flew through the defences while German radar operators watched helplessly, unable to distinguish real targets from electronic ghosts. The Kammhuber line, which had achieved reasonable effectiveness against small, scattered raids, collapsed completely against large, concentrated attacks supported by electronic countermeasures. German night fighter losses increased while their kill rates declined. Luftwaffe night fighter pilot morale, previously high despite increasing danger, began to erode. The RAF, meanwhile, continued improving AI radar technology. AI Mark 10, an American design designated SCR 720 in US service, and adopted by the RAF under Lend-Lease, offered further improvements in range and reliability. Later variants included lock-follow features that allowed automatic tracking of targets, reducing operator workload and making successful interceptions easier. The technology that had been unreliable and temperamental in 1940 had become, by 1944, extraordinarily sophisticated and reliable. Failure. Rates that once exceeded 50% had dropped below 10%. Radar operators who once required months of training to achieve minimal proficiency could now become effective after weeks of instruction. Aircraft that once carried one radar set now sometimes carried multiple radar systems for different purposes. AI radar for finding targets, tail warning radar for detecting enemy fighters approaching from behind, navigation radar for finding bases in poor weather. The transformation was complete. Night fighting, which had been an art practiced by pilots with exceptional eyesight and reflexes, had become a science dominated by electronics and technology. The German night fighter force, despite possessing excellent aircraft flown by brave and skilled pilots, fought at an overwhelming disadvantage. They hunted with technology inferior to what the RAF had fielded and then abandoned 3 years earlier. They faced an enemy whose radar could detect them before they could detect bombers, whose electronic countermeasures could blind their radars completely, and whose intruder aircraft hunted them using their own radar emissions as beacons. The statistics told a story of technological dominance translating directly into operational results. In 1940, German night fighters claimed 42 RAF bombers against minimal losses, representing approximately 10% of total bomber losses. In 1941, with AI Mark IV and GCI becoming effective, German claims increased to 421 but represented only 38% of total bomber losses, the remainder falling to flak, accidents, and other causes. In 1942, as Liechtenstein-equipped German fighters appeared in larger numbers, claims reached 687, representing 46% of bomber losses. This represented the peak of German night fighter effectiveness. From 1943 onward, as AI Mark VIII equipped mosquitoes, serrate detection, systems, and window jamming devastated German defences, the exchange rate shifted dramatically in favour of the RAF. In 1943, German night fighters claimed 1,816 RAF bombers, representing 77% of bomber losses. The absolute number was high, but so were bomber sortie rates. The percentage of bombers lost per sortie actually declined as electronic countermeasures became effective. In 1944, German claims reached 2,235, representing 91% of bomber losses. This seemingly impressive figure reflected primarily the declining effectiveness of German flak as bomber tactics evolved and the increasing dominance of night fighters as the primary threat. But the absolute loss rate per sortie continued declining because Bomber Command flew vastly more missions. More significantly, German night fighter losses climbed steeply as mosquito intruders exacted an increasing toll. By 1945, German night fighter effectiveness had collapsed completely. Fuel shortages, lack of trained crews, and overwhelming Allied air superiority reduced the Luftwaffe night fighter force to irrelevance. Meanwhile, German industry attempted desperately to close the technological gap. Advanced radar systems were developed, including SN2, which operated at longer wavelengths less vulnerable to window jamming. New night fighter aircraft appeared, including the Heinkel He-219, arguably the finest purpose-built night fighter of the war. None of these developments arrived soon enough or in sufficient numbers to alter the strategic outcome. Germany had lost the electronics war, and no amount of courage or tactical skill could overcome that fundamental disadvantage. The broader strategic implications extended beyond night fighting. The cavity magnetron that enabled AI Mark VIII also powered the H-2S ground mapping radar used by bombers for navigation and target identification. This same technology enabled the ASV Mark III radar that devastated German U-boats in the Battle of the Atlantic. Microwave radar equipped naval vessels, providing fire control systems of unprecedented accuracy. American development of the SCR-584 anti-aircraft gun-laying radar, also enabled by cavity magnetron technology, created an anti-aircraft system so effective that German pilots referred to it with something approaching terror. The technological advantage created by early British radar development, shared with America through the Tizard mission, had cascaded across every domain of electronic warfare. By 1944, Allied forces possessed electromagnetic eyes that saw through darkness, clouds, and weather. Axis forces, despite frantic development efforts, never closed the gap. The story of AI radar's evolution from unreliable laboratory curiosity to war-winning weapon system illustrates several profound truths about technology and warfare. First, Initial unreliability does not doom a technology if the fundamental concept is sound and development continues. The AI Mark II was spectacularly unreliable, yet the principle was correct. Persistent development, learning from failures, solving technical problems one by one, eventually produced systems that were both effective and reliable. Second, technology alone is insufficient. AI Mark IV was a vastly superior radar compared to Mark II, yet interception rates remained abysmal until ground control interception radar provided the necessary precision control. The system worked only when multiple technologies were integrated effectively, when crews were properly trained, and when tactical doctrine evolved to exploit technological capabilities. Third, technological advantages compound over time. Britain's 2-year head start in airborne radar development became, by 1944, an effectively insurmountable lead. German attempts to catch up consumed resources that could have been used elsewhere while never achieving parity with British and American capabilities. Fourth, superior technology creates psychological effects that transcend physical capabilities. German night fighter pilots in 1944 faced technical capabilities they could neither match nor counter. This knowledge, the certainty that they fought at a fundamental disadvantage, eroded morale and effectiveness. Conversely, RAF night fighter crews operated with the confidence that comes from possessing superior tools. Finally, wartime technology development follows different rules than peacetime development. The pressure of operational necessity drives innovation at rates impossible in peace. The cavity magnetron went from laboratory demonstration to mass production in less than 2 years. AI radar evolved through 8 major versions in 4 years. Solutions that would have taken decades to develop during peacetime appeared in months because failure was unacceptable and resources were essentially unlimited. The physicist Taffy Bowen, who began the AI radar project in 1936 as a young researcher working with temperamental equipment that rarely functioned, lived to see his technology become the foundation for entire categories of military electronics. He emigrated to Australia after the war, helping establish that nation's radio astronomy capabilities. Many of the scientists and engineers who worked on wartime radar development went on to distinguished careers in academia, industry, and government research. James Van Allen, who developed rugged vacuum tubes for American proximity fuses, became one of the founding figures of space science with his discovery of Earth's radiation belts. Luis Alvarez, who invented phased array antennas for radar applications, later won the Nobel Prize in Physics for his work in particle physics. The intellectual capital developed during the AI radar program helped establish Anglo-American leadership in electronics and computing throughout the second half of the 20th century. The industrial infrastructure created for radar production found new uses after the war. Factories that manufactured magnetrons converted to producing television tubes and consumer electronics. Workers trained in precision electronic assembly became the workforce for the emerging electronics industry. Techniques developed for radar production influenced manufacturing across multiple sectors. The story's conclusion circles back to where it began, with the question of reliability. The AI Mark II radar that equipped Bristol Blenheims in 1940 was genuinely unreliable, failing more often than it worked, frustrating crews and commanders alike. Yet that unreliable equipment contained the seeds of technologies that would transform electronic warfare. The engineers who struggled to make crude vacuum tubes survive the rigors of flight learned lessons that enabled increasingly sophisticated systems. The operators who mastered interpreting ambiguous displays on primitive scopes developed training methods that accelerated proficiency for subsequent generations. The pilots who learned to coordinate with radar operators established tactical procedures that evolved into standard doctrine. Every failure, every frustrating sortie where equipment malfunctioned, contributed to understanding how to make the technology work. By 1944, AI radar had become so reliable that crews depended on it absolutely. A radar failure was considered an aircraft malfunction requiring return to base, not the routine occurrence it had been 4 years earlier. The transformation from unreliable novelty to essential tool was complete, For German fighters, this transformation meant technological blindness of the most complete kind. They possessed radar, but it was radar that the enemy could detect and jam. They possessed skilled pilots, but skills could not overcome the advantage of seeing enemy aircraft long before being seen themselves. They possessed brave crews who continued fighting despite knowing they faced enemies with superior capabilities. But courage and skill proved insufficient against opponents who saw perfectly while they remained blind. The one engineer's unreliable radar, derided by skeptics in 1940, had indeed made German fighters completely blind by rendering their technological capabilities obsolete and their tactical options non-existent. The electromagnetic spectrum, invisible to human eyes, had become a battlefield where victory went to those who could see farthest and most clearly. Britain had won that battle decisively, and the consequences extended far beyond night fighting to shape the course of the war. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.